So we're going to talk about today, in this video, about minimums and maximums and what are minimums and maximums. Minimums and maximums are very important in calculus. They're also very important in physics and in engineering. So they're very important concepts, and we need to kind of define what they are. So first off, a minimum or a maximum. So let's talk about what we call absolute max. An absolute max, F, has an absolute max at C if f of c is bigger than or equal to f of x for all x in the domain. An absolute min, similarly, is that f has an absolute min at c if f of c is less than or equal to f of x for all x in the domain. We're going to talk a little bit more about what that means, but let's define a little bit more. Before we do that, I do want to point out that f of c is the max or min value, not c itself. C is where it occurs, but the function value is the actual max or min. So another concept we need to talk about is what is called a local max. So f has a local max at c if f of c is bigger than or equal to f of x when x is near c. And f has a local min at c if f of x is less than or equal to f of x. Sorry, if f of c is less than or equal to f of x for x near c again. So let's talk about what this difference is between this absolute and this local. In my town, I have a mountain that's near me. It's the San Francisco Peaks, and it's the maximum near us. It's the highest point near us. It's 12,000 feet. It's the highest point we go to. However, it's not the highest point in the United States. The highest point in the United States is Mount McKinley or Mount Denali in Alaska. And the highest point on the Earth, that's not even the highest point on the Earth. The highest point on the Earth is Mount Everest. And so the absolute max on the Earth is Mount Everest. But for me locally, Mount Humphreys is the closest, is the highest point. San Francisco Peaks is the highest point for me locally because it's near me, and it's near me. I'm looking at it locally. So the absolute is not the same as the local in this case. My absolute max would be Mount Everest. For those who live near Mount Everest, by the way, their local max and their absolute max are the same because they live near Mount Everest. Same thing with local min. For me, local min is the Phoenix Valley area because it's the lowest point near me. It's certainly not the lowest point in the United States. The lowest point in the United States is Death Valley. And that's certainly not the lowest point on the Earth. The lowest point on the Earth is the Marianas Trench. But it still gives you an idea of locally, that's a low point for me. But globally or absolutely, it's something different. So local is just near me, but it doesn't mean it's always your absolute. So here's an example to kind of show you these concepts. I have a function that's going to go start at some closed point here, come down, then go back all the way up, and then comes back down to a closed point. So what I want to know is where does it have an absolute max occur? So again, we're going down, so that's not a max. And then we're going to go up, and we get up here to this up. And that highest point is your up point, and that occurs when x equals 3. So the absolute max occurs when x equals 3. It's not the maximum value. The maximum value is the y value, which we don't have the y values on our axis here. But we do have what the x value is. So we do know where it occurs. We just don't know what the value is. But it occurs at x equals 3. Then we don't want to know where it has an absolute min. So again, we start here. We come down. We go up, and then we come back down again. But at x equals 5 is that lowest down. It's below when x equals -1. So x equals 5 is where that absolute min occurs, because that's the lowest point on this interval. We also want to know, where does the local max occur? With a local max, again, if I start here and come down and go up, near this point at x equals 3, that's my local max also, because that's the highest point I'm going to have near this x equals 3. There's nothing else. Here at x equals 2, it looks like it's a max. Well, not really. It doesn't look at all like a max, but you can notice this number is bigger than it. This number is smaller than it. But at x equals 3, there's no numbers bigger than it. It's just numbers smaller than it. So at x equals 3, we have a local max. It also is the absolute max. So the absolute max and local max can occur at the same place. Local min, again, we're coming down, and at x equals -1, notice that's the lowest point. There's numbers bigger than it on both sides of -1, but at -1, that's the lowest point there. So at x equals -1, we also have a local min. Now, I don't include the endpoints in this discussion because I don't know what's happening at -2. At -2, I don't know what's happening on the other side of it because it started there. So I can't know for sure that that's my highest point near -2 because I don't know what happens on the other side. Same thing with at 5 here. I don't know what's happening here. So I can't say that 5 is where a local min occurs because I don't know what happens beyond 5. So we only look at where we can actually tell what's going on around them for our local max and mins. Now, there's a theorem that I want to talk about. It's called the extreme value theorem. And it says if f is continuous on some closed interval from a to b, then f obtains an absolute max value, f of c, and an absolute min value, f of d, at some numbers c and d in AB. And so this is actually what we call an existence theorem. It just tells me they will be them. They will occur, so go look for them. So we like existence theorem because it tells us to go look. But let's talk about what we mean by this. So I want to look at some graphs of this. So the first graph I'm going to look at, here's my A and here's my B. I'm going to start at A. It's closed interval, so it's got a dot there. I'm going to come up. I'm going to come down. And then I'm going to come back up to B. Notice that I do have a point where it's the highest point at all. It has the maximum Y value. It's going to be there. That is point C. I also came down, 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 down. This has a lowest point. The lowest point here, that Y value will be the lowest point that occurs at D. So notice there is some C and some D in this interval from A to B where those occur. So that, again, goes with that existence theorem. Another graph I want to look at, again, here's A and here's B. And I might start here at A, go up, and then come back down to B. While looking at this, again, I see I went up. That up point is my maximum point. It occurs at some point C. I then come back down and I come all the way down to where B occurs, where B is. That value, if I come over my y-axis, that value is my lowest y value in this interval. So it occurs at B. So B and D are the same in this case. My local min occurs at B. I'm sorry, my absolute min occurs at B. And so that works beautifully for that. And so notice that your max can occur at the endpoints or it cannot, but it's still existing there. One more graph I want to look at. Again, I'm going to have some point here A and some point here B. And I'm going to come up. I'm going to go down. I'm going to come up. I'm going to go down and I'm going to come and I'm going to hit B. I messed up my B a little bit. Noticing that I have a place where I have a minimum. This lowest point here, that's my lowest point I'm going to get. My B is a little bit above that point. That's my lowest point. So that's my D. That's the lowest point it's going to be. However, I have some high points here, 2 high points. They have the exact same Y value. So they both have the same Y value. So those are both absolute maximums because again, the absolute max is the Y value. So they occur at these 2 different values. I can't call them both C, so let's call this one C1 and this one C2. So they still occur, but there's 2 of them, and that's okay. I do want to show a couple more examples. These examples are about the whole idea that it has to be continuous on some closed interval. So again, here I've got my A and here I've got my B. And I'm going to have it still be closed. But I'm going to come up from A and I'm going to head up to some number and I'm going to be open. And then I'm going to drop down to a different spot where I'm going to start. And then I'm going to come down from that point to B. And I'm still going to be closed. So this graph, if you notice, was not continuous because I went up and I came back down. So we're not a continuous function. And I don't know what my maximum y value is because it's an open circle. I don't know what the actual y is. I know where it's heading, what the limit of that is, but I don't actually know what that absolute maximum value is. So there is no max, no absolute max. There's also probably no local max in this case, but there's definitely no absolute max. Minimum, I have, again, we don't look at the endpoints in terms of local mins and maxes, but I do notice I have what we consider an absolute min here at B. So that's where the continuous part comes in. It's very important that it has to be continuous because I don't have an absolute max. I do have an absolute min at the endpoint, but only because it's a closed interval. So that brings me to one more example. Here again is A, and here again is B. And I'm going to come from A, but I'm going to be open here at A. I'm going to come up and I'm going to go down, and B is actually an asymptote. So in this case, I do have, it looks like an absolute max, but I have no guarantee of an absolute max because of this, but I also have no absolute min. I do have an absolute max right here, only because of the way the graph drew, but I had no guarantee of that, but I don't have an absolute min. Okay, so the next thing I want to look at is what we call another theorem. It's called Fermat's theorem. This is not Fermat's last theorem. Fermat's last theorem was actually a theorem he came up with where he had some idea, and he said the theorem was really easy to prove, but he didn't have room in the margin, so he didn't prove it. And so it was never proven. It actually took a couple centuries to prove, so it wasn't an easy proof. It was just proved in the 1990s by Andrew Wiles, and it was not an easy proof. So it took him like 9 years to prove it. So, but this is a different theorem of his, and it says if F has a local max or min at C, and F prime exists, then F prime of C equals 0. So first off, F prime of C equals 0 does not imply that F has a local max or min there. It just says that there is actually, these are possibilities. It also doesn't say anything about if F prime doesn't exist, what happens. So you could have a local maximum in there. We don't know for sure. But these are just suggestions of places you can try it. So you can look at where is F prime equal to 0, where is F prime not existing, and then look to see if those are local maximins. But if you know for sure it's a local maximin, then you know that the derivative exists there and it's 0. So to show you kind of what this talks about and what we mean by this is, I'm going to draw a couple graphs here. This is the graph of x cubed. So f of x equals x cubed is this graph. At the origin right here, and I didn't draw a very good graph of it, but at the origin right there, the derivative is 0. So at that point, f prime of 0 is in fact 0. But notice that's not a local maximin. So this is what this theorem is saying. If it was a local maximin, we know the derivative would be 0 there. But because it's not a local maximin, we even though the derivative is 0, it's not necessarily a local maximin. To show you kind of what this means is, let's go back to these pictures here. This one here is a local, it's actually an absolute, but it's also local max here. Notice the derivative would be 0 there. It's the local min. Notice the derivative would be 0 there. So that's just what it's saying. But this is just telling you, hey, just because it is 0 doesn't mean it's a local maximin. So this is an example of that. Another example of that is in this case, this is the graph, is the V-shaped graph. This is the graph of x squared. I'm sorry, not x squared, of the absolute value of x. So this is the graph of the absolute value of x. And notice here, it does have a local min, but because this is the lowest point around near that point. But f prime of 0 does not exist. And that's because we have a corner there, and you can't have corners and have it exist. So these are, again, are just places where you could have it happen. And that gives us to another concept called a critical number. A critical number of a function is a number c such that f prime of c equals 0, or f prime of c does not exist. So these are places where we're going to look at, we're going to find these. C happens to be in the domain of f, so make sure it's in their domain. And so let's look at an example of finding these. So let's find the critical numbers of g of x equals the cube root of x squared minus x. So first off, I don't like writing cube roots. Let's write this in exponential form. So it's x squared minus x to the 1/3. And then we can find the derivative. So take the derivative of the outside, 1/3 x squared minus x to the negative 2/3. And then derivative of the inside would be 2x minus 1. Now, I like negative exponents, but sometimes they're not very useful for solving things. So let's go ahead and just get rid of it just for this one time, just to see what's happening. So we're going to have 2x minus 1 over 3 times x squared minus x to the 2/3 power. And now what I want to know is, where is this derivative of 0? Because again, that's where my critical points could exist, is where the derivative is 0. Well, the derivative of 0 when 2x minus 1 over 3 over x squared minus x to the 2/3 equals 0. Well, using a little bit of algebra here, I can just multiply both sides by the denominator, make the denominator go away. So that's actually just saying the numerator, 2x minus 1, equals 0. So that's just where x equals 1/2. So there's a critical point. So there's one critical point, but there's another critical point that could happen possibly, is where does the derivative not exist? So the derivative does not exist where 2x minus 1, actually, we don't even need to write the whole thing. We just know it's going to not exist where the denominator is 0. So this fraction is going to not exist where 3 times x squared minus x to the 2/3 power equals 0. So notice this is basically akin to the idea of just setting the numerator equal to 0 to find out where one critical point, set the denominator equal to 0 to find the other one. If you have denominators and numerators, but this is kind of the process. Solving this, divide both sides by 3, raise both sides to the 3/2 power. You get 0 squared minus x equals 0. X, pull the x out, so you get x times x minus 1 equals 0. So x equals 0 and x equals 1. So here's your 3 critical points. X equals 1/2, x equals 0, and x equals 1. So that's great. We now have these critical points. We have all this information. Now we can actually find these absolute extrema. Absolute extrema are the idea of, extrema just means max or min. And so we want to find those. We're going to use what we call a closed interval method. We'll look at open intervals later. But the closed interval method says A is continuous function f on AB. So it, again, must be continuous. We must be on a closed interval so that we can use the idea of that one, the extreme value theorem that tells us that there will be some. Then we're going to find the values of f at those critical numbers in AB. So look for those critical numbers, find out what those critical points are, find those critical numbers, and then evaluate the function at those points. And only the ones that are in that open interval from A to B. We don't need to worry about the endpoints just yet. And you also are not going to look at any critical numbers that are not in that interval. Then you're going to find the values of f at the endpoints. So we're not ignoring the endpoints. The endpoints are very important. We're going to first find the critical numbers at the we can find the function value at the critical numbers, and then we're going to find the function value at the endpoints. And then here's the easiest part of this. The largest number is your absolute max. The smallest number is your absolute min. And that's all it is. So you just look for the biggest number and the smallest number. So let's find the Abs Extrema for f of x equals x over x squared plus 4 on the closed interval from 0 to 3. So again, first thing I need to do is find these critical numbers. So I need to find the derivative. You can use the quotient rule. You can make this into negative exponents and use the product rule. I don't really care what you want to do. Anything you want is fine, just find the derivative. I'm going to go ahead and use the quotient rule. So the derivative of the top is 1 times the bottom minus the top times the derivative of the bottom, which is just 2x, all over x squared plus 4 squared. All right, so let's simplify this a little bit just to make it a little bit nicer to work with. So that'll be, there's an x squared here minus a 2x squared, so that's a minus x squared plus 4 over x squared plus 4 quantity squared. Now we're going to look at where is that derivative 0. So again, that derivative is going to be 0 since it's a fraction. It's just when the numerator is 0. So that's going to be when x squared equals 4. So x equals plus or minus 2. The other thing we need to look at is where is the derivative not existing. So the derivative does not exist when your denominator is 0. Well, in this case, x squared plus 4 will never be 0. So this is none. I'll just say never. So it never can happen. So there will be no more critical numbers. So my only critical numbers in this case are plus or minus 2. However, we are on the closed interval from 0 to 3. So -2 is not in that interval. So when we go to look for the absolute max, we don't need to look at that -2. So we only need to look at what is the function evaluated at 2. So again, our function was x over x squared plus 4. So it's going to be 2 over 2 squared plus 4. So it's going to be 2 over 8 or 1/4. Then we also need to look at the endpoints. My endpoints were 0. So f of 0 would be 0 over 0 squared plus 4. That's 0. My other endpoint was 3. So it'd be 3 over 3 squared plus 4. And that's going to be 3 over 13. And now, again, here's the easy part. The biggest number is your absolute max. The smallest number is your absolute min. So here's 0. There's my absolute min. Make sure you note that. Now we have to look at my absolute max. We have 1/4 and we have 3/13. 1/4 is 3/12. So 3/12 is bigger than 3/13. So here is my absolute max. And that's it. We're done.